In this presentation, I will present information regarding the grid characteristic of frequency and how frequency affects a radiographic image. To review, grids have three general characteristics. They are ratio, frequency, and design. While ratio has the greatest effect on fog removal, the possibility of grid errors, and patient dose, frequency is a minor role in the quality of the recorded image. It is important for imaging professionals to understand frequency's impact on finished radiographs. Due to my lack of artistic ability and a wish to keep things simple, some of my demonstration slides will not include a patient or X-ray tube, just the radiation beam, the grid, and depiction of the final image are shown. Let's place a grid over the imaging plate in an effort to reduce scatter reaching the plate. While the grid allows most of the remnant radiation to reach the imaging plate, a small amount of radiation strikes the lead strips on edge, and the lead strips are recorded as part of the image. For the sake of illustration, my lead strips are white and very large, so they are easy to visualize. If you can't say that you've ever seen grid lines on an image, they were hidden or obscured by the manufacturer of your equipment by one of two methods. The first method for hiding grid lines is to make them small. Small things are harder to see. We are building two grids, both have the same ratio, but they have different number of grid strips per inch. Since the ratio is the same, both grids will clean up scatter equally and have about the same margin of error. This characteristic is called grid frequency. As the second grid is built, it takes twice as long to construct. For this example, it is easy to see that the high-frequency grid will be more costly because it requires smaller materials and more exacting precision in its construction. Since lead strips are thinner and interspaces are closer together, they are more difficult to see. The grid below has twice the frequency as the one above. Lead lines are smaller and closer together, and as a result, harder to visualize. Frequency determines the visibility of grid lines and greatly affects the cost of a grid. Frequency is commonly measured in lines per inch or in lines per centimeter. Grids range in frequency from 50 lines per inch to 150 lines per inch. Grids over 100 lines per inch are considered as high frequency. Low frequency grids are usually used in applications where they can be reciprocated. More about reciprocation in a minute. While frequency does affect grid performance, ratio has by far the greatest effect on cleanup. Radiographers must be cautious when evaluating the impact of new grids by viewing images using inexpensive monitors, like the ones included with most radiology systems. These monitors don't have the resolution to demonstrate high-frequency grids. To do a proper evaluation of a grid's impact on the image, a radiologist's workstation must be used. So, a quick comparison of grid frequencies is: high-frequency grids have more lines per inch and are more expensive to manufacture, the benefit being that lead strips are less visible on the final image. Low-frequency grids are less expensive and are used in bucket applications where the grid can be reciprocated. While high-frequency grids can obscure grid lines, there is an alternative method for removing grid lines from an image that allows a much cheaper low-frequency grid to be used. This method uses the principle of motion to blur out the grid lines. It involves moving the grid across its width during the exposure. Reciprocation causes grid lines to virtually disappear from the image. The grid moves before the exposure begins and continues to move after the exposure terminates. The motion of the grid lines blur out the grid lines and completely eliminate them from the final image. Do some of your stationary grid images appear with superimposed jagged and/or dark bars on the image, like the image below? This artifact is called a moire pattern and is related to the frequency of the grid along with the grid's orientation. Moire patterns occur when two parallel line patterns overlap and one or both of the patterns are slightly tilted relative to one another. Here is a line pattern caused by a grid and another line pattern contained in a CR image produced by scanning pattern of the CR image's laser. If the two patterns are held in strict alignment, then superimposition is no problem, and no interference is observed. Moire artifacts occur when two line patterns are slightly angled relative to one another. When the two patterns are superimposed, an interference pattern is produced, and this artifact is called a moire pattern. Note the dark jagged lines caused by the misalignment. There are two ways to eliminate moire patterns on an image. One is to swap out the grid for one with a higher frequency. The other is to turn the grid 90 degrees so the grid lines run perpendicular to the computer scanning pattern. On 25, the 10 by 12 cassettes are scanned parallel to the length of the cassette, and the 14 by 17s are scanned parallel to the width of the cassette. For CR systems, it is important to know the scanning orientation of your digitizer when dealing with a moire artifact. Thank you for your kind attention. This is the end of the grid frequency presentation.